So now with gravitational potential energy under our belt, it's a very useful thing and very common thing in standardized tests such as the MCAT to look at the conservation of energy. And the conservation of energy says that the energy initial is equal to the energy final. So for conservative forces, I'll put this as a parenthetical, for conservative forces, that means primarily when we're dealing with gravitational potential energy and we're neglecting all friction, which we can do in a lot of cases, that this initial energy is equal to the final energy. And then so we can extend this, we can say that the kinetic energy initial plus the potential energy initial, assuming that these two make up the total energy of an object. That is, it's the energy that it has associated with motion and the energy that it has associated with the potential for motion, that the sum of those is equal to the kinetic energy final plus the potential energy final. And that's assuming only conservative forces, because if you have non-conservative forces, then you're going to have energy that is dissipated or lost into the environment in the form of thermal energy, like when you have frictional forces, things heat up and all that jazz. All right, so let's look at an example. Very common types of problems. Consider for this scenario, I have a mass of 100 kilograms. I have this object right here. It has a mass of 100 kilograms. We'll take g to equal 10, and its initial speed is 10 meters per second. So it has a speed moving on this track of 10 meters per second. And I know that it moves over a bump, h over 2, and then it comes up to a height of h. All right, now first I want to find out what is h. What do I ask myself at each of these scenarios is what is the potential energy and what is the kinetic energy? What is the potential energy? I'll call this h over 2. And what is the kinetic energy? And then what is the potential energy? And what is the kinetic energy? I'll call this at h. You want to ask yourself that question for each position, and then you want to realize that the sum of those at any particular position is the same at any other position. So for example, here, I know that the potential energy is equal to 0 because h equals 0. And I know the kinetic energy is 1/2 mv squared. And I know its mass and I know its speed. So I'm not going to put any numbers in just yet. Now over here, I know that the velocity or the speed equals 0. So the kinetic energy equals 0. And I know then that my potential energy equals mgh. So I can say this sum of energy, that is 0 plus 1/2 mv squared, equals mgh plus 0. That is equal to the sum of these energies. And then I can use that to solve for h. But notice that my masses cancel. So while I give you the mass here, the mass is irrelevant. And I can solve for h. So I have h equals 1/2 v squared over g. V was 10, so it's half of 10 squared, or 50. It's going to be meters squared per second squared, over g, which is 10. Gives me 5 meters. So I know then that h, that the object comes to rest when it comes up to 5 meters in height. Okay. Now, I also want to know what is the speed at h over 2. What is the speed at h over 2? So here at h over 2, I know that h over 2 is 5 over 2, so 2.5 meters. So I can tell what is my potential energy, mg h over 2. I can also tell what is my kinetic energy, 1/2 mv squared, but I want to solve for this speed. All right, so you can do this in any way. I will take my initial energy and set it equal to my energy at h over 2. And that's going to be 0, which is my potential energy, plus 1/2 mv v, I'm going to call it v naught squared, equals mg h over 2 plus 1/2 mv squared. And I'm looking for this v. Notice my masses cancel. I want to solve for v. Oh, also notice I can cancel out these 1/2 values because they're in all three terms. And so I have v naught squared equals g times h plus v squared. So v is equal to v naught squared minus gh. Square root of that is going to be the square root of 10 meters per second squared minus 10 meters per second squared. That's g times h, which was 5 meters. I notice, I had actually, my height is 2.5 meters, which I had here, but that 2 canceled out. So here, I'm just considering the variable h. This is just algebra. So that's going to be the square root of 100 minus 50, which is the square root of 50, which is about 7 meters per second. Okay. And now I also want to know what is v at point C. Let's see, was that labeled on my figure? No. I want to know what is v at point C. And at point C, my height is h over 3. Notice, by the way, that my velocity at this point, which is at a similar height, would be exactly the same. Likewise, over here at h over 3. My velocity at each of those points would be exactly the same as long as they're at the same height. All right, so what is my v at point C? Well, I'll just take the same tack that I took up here. It's basically the same problem. 0 plus 1/2 m v naught squared equals mg h over 3 now, because I'm looking for a new height, plus 1/2 mv squared. And I'm looking now, just as I was before, for v. Can do this. I'm going to do it in a slightly different way. Since I know the mass, I'm just going to say, well, I know what my original energy is, because my mass here is 100 kilograms. So I can say 1/2 times 100 times v naught, which was 10, squared. Actually, no, I'm not going to do that. Leave out that 100. Sorry, that'd be silly to do that because my masses cancel all the way throughout. But I have 50 equals 10 times h over 3. H is 5 over 3 plus 1/2 v squared. And I solved that for v, and this is going to be my speed at the position h over 3, and that's going to equal 8 meters per second. It's the square root of 67, which is approximately 8 meters per second. Okay?